All right, we're back with part 2 of our third lesson into equilibrium, looking at solving problems involving equilibrium and ice tables. So hopefully after you tried following along with problem 1, you'll be able to understand a little bit more about the next two problems. So let's take a look at the question together, and this time I'm going to let you start solving some of the problem on your own as you work through it along with me. So the following reaction has a KEQ of 25 at 1100 degrees Kelvin. 2 moles of hydrogen gas and 3 moles of iodine are placed in a 1 liter container. What are the equilibrium concentrations? So we have a similar type of question as before, but a little bit different numbers and scenario. So KEQ is 25. We're going to use that a little bit later. That's our equilibrium constant. And we have initial amounts for both of our reactants, 2 moles and 3 moles respectively of hydrogen and iodide. They're placed in a 1 liter container. To find their concentration here, we're going to do the same thing. C is equal to N over V, but this time it's nice and easy because we've got a 1 liter container, so we really don't need to do any math. We're dividing our moles by 1. And we're doing the same thing this time, solving for equilibrium concentrations. So I want to see if you first can set up the ice table for this problem. I want you to pause the video at this point and see if you can fill in the ice table based on what we learned in the first example. So pause the video, give it a try, and once you've filled it in, unpause and we'll check our answers. So hopefully you gave that a shot. Let's take a look. So 2 moles in 1 liter is 2 moles per liter. So 2 for hydrogen. 3 moles in 1 liter is 3 moles per liter for iodine. Nothing was said about our product, so that starts off as 0. Same scenario as before, we've got some of our reactants. They're going to be converted into products. So they're both going to lose, and we're going to hold on to the same mole ratios. 1 mole of hydrogen, 1x. 1 mole of iodine, 1x. We're going to produce some product or gain product. So the sign here is positive, but what's different from the previous example, we have a coefficient of 2. That means 2x. That's our mole ratio part if we're comparing to grade 11. Then for the equilibrium concentration, we're combining the first two. So 2 minus x, 3 minus x, and then just 2x. So hopefully you had a chance to try that ice table and were overall successful filling that in. Once you've done it a couple of times, it gets pretty standard and straightforward. Okay, so same scenario here. We want to find out what's the equilibrium concentration. So to get there, I need to find out x to fill in that last column. So guess what we're going to do next? Write out another KEQ expression. So again, I want you to try this. Pause the video right now and see if you can write out the KEQ expression and then fill in the right values from our ice table into that KEQ. So go ahead and pause. So let's check your answers and see how you did. First, our K expression. Our products always go on the top. When there's a 2 or any number for the coefficient, it becomes your exponent. So don't forget to put it in here. It needs a 2 as the exponent. On the bottom, we have 1 mole of each of our reactants, so they just have an exponent of 1. Next, what you're going to do is fill in your equilibrium concentrations and the KEQ. So back in the question, the KEQ was 25. That was given to us. 2x, that's going to go on top. And then on the bottom, 2 minus x and 3 minus x. And again, at this point here with the star, all you need to do is solve for x. All math until the very end when we have to summarize what x means. Now, this scenario is a little bit different than the one previously. We could use that trick where we were taking the square root of everything. But taking a look at this is definitely not an option. So guess what? You're going to have to go back and use your good old quadratic equation. Now, just to make sure everyone remembers what it is, I'll make a little note here on the side. X is negative b plus or minus square root of b squared minus 4ac all over 2a. And to get everything in that format, you have to simplify your equation into ax squared plus bx plus c is equal to 0. So again, I'm going to want you to pause the video and see if you can use some of your math skills to start to solve for x, first putting it in proper format, and then plugging it into the quadratic equation and solving for x. So pause the video and try that out. Now that you've had a chance to try and solve for x, let's walk through a couple of the steps together. I'm not going to show every mathematical step, but I'll show a couple. So 2x, the whole thing squared, make sure you get 4x squared on the top. And when you expand through all of your brackets, you should get 6 minus 5x plus x squared. When you multiply through and group all like terms, you should get 21x squared minus 125x plus 150 is equal to 0. If this type of math is giving you some trouble, go back, search, ask your math teachers for some questions on quadratic equations. Or what you can do at the very beginning of the chapter on equilibrium for this unit, there are some unit preparation questions, and there are a couple in there that are just math-based, solving for x, multiplying. You could try those out and check the answers if you need some more help with this. After you've got that into your proper format, then comes the actual quadratic equation. So again, I'm going to plug it in, but I'm not going to show every calculation step. You take as many steps as you need to. But when we put it all in at a minimum, when you're showing work, make sure you show this so that I know and you know what you're doing. And then if there's any mistakes at any point, that I can follow along with any errors that you have. So when you do all of your math, you're going to get two values for x. One should be about 4.28, or x is going to be about 1.67. Now, this is going to happen with the quadratic equation. You're going to get a couple of different answers. So this is where you need to put your thinking hat on and go back and think about, well, what is x? What am I trying to solve for? And see if the numbers are actually logical. One of them makes sense and one of them doesn't. So let's go all the way back up to our ice table. So up here, remember, we have to put x in here. If we're just multiplying 2 times x, either of those numbers are positive and would work. But only one of the numbers makes sense up here for our equilibrium concentrations for our reactant. What if we used 4.28? 2 minus 4.28 or 3 minus 4.28, those would give us negative values, which mean a negative concentration. That doesn't really make much sense when you're dealing with a reaction. Reactants, you can't have a negative concentration. But what if we used 1.67? That would still give us a positive number for both here. So in this case, when you're trying out the equilibrium problems and you're using quadratic equation, one of them will work and usually one of them won't. So 4.28 does not work, but 1.67 does. After you've sorted out your x value, you want to go back and again solve for the concentrations at equilibrium. That's what the question wants you to do. So 2 minus x for hydrogen, so 2 minus 1.67, and that's going to give you 0.333 moles per liter, and you want 3 significant digits here. Then you're going to do the same thing for iodine. Oh dear, clicking all the wrong buttons. There we go. Iodine, so 3 minus x, so 3 minus 1.67, that'll give you 1.33. And then, of course, don't forget about your product. So for hydrogen iodide, this is the easier one for most people. It's 2x. So 2 times 1.67, and that's going to give us 3.34 moles per liter. So problem 2 is similar to problem 1, where we're solving for a concentration at equilibrium. We have to solve for x. One involves quadratic equation, the other one you can use a little trick to get out of it, but quadratic equation would actually work for both. But one thing that is common between problem 1 and problem 2, which you may not have noticed before, but we'll highlight now, both of these ones have large k values. So problem 2, k value is 25, that's greater than 1. If we go back to problem 1 for a minute, the one we just solved previously, this also has a k value greater than 1 at 8.3. If you remember when we talked about k values from lesson 1, if k is greater than 1, it's going to favor the products. So when we look at our actual calculations, that means that our products are going to have a higher concentration than our reactants. So let's scroll back down to the problem that we just solved. Hydrogen and iodide, they have lower concentrations than our product, which is the hydrogen iodide. 3.34 is greater than the other two concentrations. So with a KEQ, remember we said for this problem was 25, it's emphasizing that at equilibrium, your product concentration is larger than the reactant. So same thing if you go back and flip to problem number 1, you should notice that your products have a higher concentration than your reactants. The last problem that we're going to take a look at has a different K value. It's a smaller K value, and that's one that's a little bit different than these two examples. So let's flip to the last problem, and we have to use a special method to solve this one. But let's just do a quick review again of K. So what happens when KEQ is less than 1, so a small number? That means the equilibrium is going to favor the reactants. Favors the reverse direction, it lies more to the left, any way you want to describe it. So it means there's going to be more reactants at equilibrium. So when we look at solving these problems, we know that change in equilibrium is only going to be a small value. That x value is going to be small. So how we tackle these problems is a little bit different. We use something called the approximation method. So let's go over just what it means and what the rule is, and then we'll try it out with a problem, and hopefully that'll help you understand a little bit more about what's going on. So the approximation method says when KEQ is small, when you're comparing it to your initial concentrations, you can essentially ignore that x value. So what that means is if you have something like this, where we saw in our ice tables where we were subtracting an x value, if the x value is very, very small, if it's very, very, very small, if you subtract that from 0.095, it's probably going to round back to 0.095. You might get a number that looks like this, 0.0949999, and so on. The number is going to be really close to the starting value. So we can essentially eliminate it or say it's going to be approximately the same concentration as what we started off with. How do you know when you can use this little trick? There are a couple of different rules you can follow. The one in your book's a little bit different, but this one I find works the easiest. If you take your starting concentration and divide it by your K value, your KEQ, if that number comes out to be greater than 100, you can use this approximation method, or we say it's justified. However, if you check your starting concentration and divide it by K and it's less than 100, you can't use this method which means, guess what? You're back to good old quadratic equation. So, avoiding the quadratic equation, because I know you all would rather not use it if you didn't have to, is a great way to get around that problem. So let's take a look at our last problem for the lesson and see how this would work. So here's our problem. We've got 0.085 moles of nitrogen and 0.038 moles of oxygen in a 1 liter container. And our KEQ value is 4.2 times 10 to the negative 8. And we want to know what's the concentration of our product at equilibrium. So the first clue here that you might see is that this is a small value. 4.2 times 10 to the negative 8. So anytime you see a small k value, whether it's these types of problems or others we'll see later, you should think approximation method is something I'm going to check. But before we get to that part, let's fill in our ice table. Now again, I want you to try this one out before we go forward. So pause the video right now and see if you can fill in that ice table. So let's check your ice table before going on. We've got 0.085 moles of nitrogen in a 1 liter container. So it's just 0.085 moles per liter. And same with oxygen, 0.038 moles per liter. Nothing with our products. We know we're going to lose some of our reactants, 1 mole, 1x. We lose some of our oxygen, 1x. And here we're going to gain some of our product, and it has to be a 2 here for 2x. Equilibrium, we combine both together, 0.085 minus x, 0.038 minus x, and 2x. So before you go on and jump into your k expression and solving for x, this is where you want to do your approximation method. So over somewhere on the side, I always like to make a little note. I'm checking my approximation method. So my approximation method said I can take my initial concentration and divide it by the k value. Now if you're given two different values for initial concentration, go with the smaller value. So 0.038 is smaller. And I'm going to divide it by 4.2 times 10 to the negative 8. Now go ahead and plug that in your calculator. Pause the video if you have to. And check, is that number greater than 100? After checking in your calculator, it's definitely greater than 100. It's a really, really, really big number. If you're good with numbers, you might have even noticed the difference in the values there will definitely give you a value greater than 100. So what that means is we can use our approximation method. So what does that mean for your ice table? Any x value, if it's added or subtracted, you can eliminate it. So this is going to be approximately 0.085 because it's subtracted. It's going to be tiny. This is going to be 0.038. But we can't change our last value here. It's 2x. We have to make some product, so we still need an x value to solve. Nothing's being added or subtracted. But now, if you take a look at what's left at equilibrium, when we go and solve for x, at equilibrium, you can just use 0.085, 0.038, and 2x in your k expression. That's a lot easier than before. So again, I want you to pause the video here, write out your k expression, and then plug in your values at equilibrium and try and solve for x. And then when you're ready to check, unpause the video and we'll continue on together. All right, so let's check how you did. Your KEQ should be nitrogen monoxide squared on the top because there is a 2, and your nitrogen and your oxygen on the bottom. And then we're going to plug in our values. So we know KEQ is 4.2 times 10 to the negative 8. We've got 2x on the top. Don't forget to square it. And then on the bottom, this is the nice part with your approximation method, 0.085 and 0.038 go in. No x's. So now when you solve for x, it's a lot easier. And when you do that, if you've checked your answer, you should get about 4.8 times 10 to the negative 6. Remember, that's in moles per liter at this point. And we need to solve for our equilibrium concentration for nitrogen monoxide. So when we're solving, we need to solve for 2x. So again, don't forget to do that at the end. I know a lot of people in math tend to stop with x, but here, make sure you go back and relate it to the problem. So 5.8 times 10 to the negative 6. We need to multiply that by 2. And that gives you about 1.2 times 10 to the negative 5 moles per liter. So in your textbook, when you're reading, this section gives you a ton of problems. There's 3 sections of questions on your outline. Each section of question pertains to problems similar to problem 1 or problem 2 or problem 3 that we just covered. So trying to do them all is an unreasonable task, and I wouldn't expect you to do that. But I want you to try a good set of questions from each of those types of problems. So try a set from the first few, from the second few, and the third few. And if you're finding them easier, go back and look for the ones that are a little bit different. They'll give you a little bit more of a challenge. So that's our lesson on calculating equilibrium from initial amounts.